A billion light years away, a star was dying, and as it died, its light began to flicker in a way that no law of physics we had could explain. It should have simply faded. Every dying star does. The fire goes out, the light dims, the story ends. This one refused. 50 days after it burned its brightest, the fading light started to pulse. Bright, dim, faster and faster. 4 beats, each one quicker than the last. Astronomers had a word for a signal that speeds up like that. They called it a chirp. Nothing about a dying star should chirp. There was no model, no equation, nothing on paper that could make an explosion tick like a clock winding up. The signal was too clean to be an accident. Something structured was hiding inside that blast, keeping time. To find out what, a team would have to reach for a theory that supernova physics almost never touches. Einstein's general relativity, and what they found at the center was the birth of the most magnetic object in the entire universe, an object so extreme that a spoonful of it would weigh 1 billion tons, and its magnetism could kill you from 600 miles away. We had theorized it for 16 years. We had never once seen one born, until a star 1 billion light years away chirped. To see why this death broke the rules, you first have to know the rules. Most massive stars die the same way, on the same schedule. For millions of years, a giant star holds a standoff. Gravity pulls inward, trying to crush it. The furnace at its core pushes back out. That balance is the star's whole life. As long as the core keeps burning, it holds the crushing weight of itself at bay. But the fuel runs out, and when the furnace finally fails, there is nothing left to push back against gravity. In less than a second, the core collapses. Matter the size of a planet falls into a ball the size of a city. Then it rebounds, and the outer layers of the star are blasted into space in a supernova, one of the brightest events in all of nature. For a few weeks, it can outshine an entire galaxy of stars. Then, as the debris spreads and cools, it fades, predictably, on time. That is the script. Collapse, explode, blaze, fade. It has played out across the sky for billions of years, but starting in the early 2000s, astronomers began catching explosions that would not follow it. They were far too bright, 10 times brighter than they should be, and instead of fading in weeks, they blazed on for months as if something kept feeding the fire. A normal supernova is a bomb. It goes off once and it is spent. These were burning like something with a fuel line. For 20 years, no one could say what that hidden fuel line was. The star 1 billion light years away was about to leave the answer written in light. The star was named SN 2024 AFAV, spotted in December of 2024. At first, it looked like an ordinary, if very bright, explosion. A global network of 27 telescopes locked onto it and watched, not for a night, not for a week, for more than 200 days. That patience is what caught it. A single snapshot would have missed everything. Only by watching the fade night after night did the rhythm appear. Around 50 days past its peak, the smooth decline broke. The brightness dipped, then rose, then dipped again. A graduate student named Joseph Farah was tracking it. He saw 4 bumps in the light, and each gap between them was shorter than the last. He had seen a pattern like that before, but never here. A signal that rises in pitch as it goes is exactly what 2 black holes make. When black holes spiral together, they send out ripples in space-time that climb in frequency right before they collide. Physicists call it a chirp, but this was not 2 black holes merging. This was the aftermath of a single exploding star. A chirp had no business being here. Farah's own words were that the signal seemed too structured to come from anything random. Explosions are chaos. This was rhythm. Something inside the wreckage of that star was keeping time and speeding up, a metronome buried in a billion-year-old blast. Chaos does not tick. Whatever was doing this had structure and spin and a clock. It was behaving less like debris and more like an engine. And an engine was exactly the word that would crack it open. The engine had a name astronomers had whispered for years without ever seeing one form: a magnetar. Picture the collapsed core left behind by the blast, not debris. A newborn neutron star, city-size, spinning hundreds of times every second. And wrapped around it, the strongest magnetic field known to exist anywhere in the universe. That is a magnetar. That was the hidden engine. Its ferocious spin and field could pour energy back into the explosion for months, the fuel line no one could find. That answered the brightness, but it did not yet answer the chirp. For that, the team needed the last piece, and it came from Einstein. After the blast, some material fell back and settled into a ring of debris circling the magnetar, an accretion disk. The disk was tilted, misaligned with the magnetar's spin, and around an object that extreme, a tilted disk cannot hold still, it wobbles. That wobble is not ordinary. The magnetar drags the fabric of space itself around with it as it spins, and the disk is towed along. Physicists call it frame dragging, a prediction of general relativity. As the disk wobbled, it passed in front of the magnetar's light, blocking and revealing it. Bright when the light escaped, dim when the disk swung across. That was the pulse. That was every bump in the curve. And as the disk spiraled inward, it wobbled faster, so the pulses came quicker. There was the chirp, explained down to the beat. It was the first time in history that general relativity was needed to explain the mechanics of a supernova. A colleague called it the smoking gun. It is worth stopping to feel what a magnetar actually is, because the numbers do not sound real. Take the mass of our sun, now crush it down until it fits inside a city. That is the density we are talking about. A single teaspoon of this material would weigh about 1 billion tons. More than every car on Earth balanced on a spoon. Its gravity is roughly 2 billion times stronger than the pull you feel right now, and its magnetism is stranger still. Your fridge magnet is 100 Gauss. A hospital MRI, 15,000. This magnetar's field was around 300 trillion times Earth's. Place one halfway between here and the moon, and it would silently wipe every credit card on the planet. Come within 600 miles, and it would tear the electrons from your atoms and pull the iron out of your blood. You would end as a cloud of nuclei. This is not a monster in a story, it is a real object, and in December of 2024, we watched one take its first breath. For 16 years, a physicist had argued these engines were what lit the brightest explosions in the sky. It was elegant and unproven. The magnetar always hid behind the debris of its own explosion. You could argue for it, but you could never point to it. The chirp was the curtain pulling back. For the first time, the hidden engine stepped forward and showed itself exactly as predicted. A 16-year-old idea, confirmed by 4 beats of light from 1 billion years ago. One explosion is a story. The real shift is what comes next. This chirp was a key, and it fits more than one lock. A new observatory is about to begin the widest survey of the night sky ever attempted, and the team expects to hear dozens more chirps like it. Each one would be another magnetar caught in the act of being born, another engine pulled out from behind the curtain. We spent 20 years unable to explain a light in the sky. Then a dying star ticked like a clock and told us the universe still has machinery we are only beginning to hear.